I'm Chen Yanzuo, and today I'll talk about our paper, OBSan and out-of-bound sanitizer to Harden DNN Executables. This is a joint work with Yuan and Professor Wang Shuai. So in recent years, we've seen the deep learning techniques, especially deep neural networks, in a very prosperous development. And today we want to deploy them in so many places that the situation has become that there are so many heterogeneous environments to handle. And at the same time, we also want to have better optimizations that are tailored to each of those platforms. So under this situation, DL compilers have emerged to be a solution. And in fact, we already have a bunch of them today. For example, we have TVM backed by Apache and Amazon, then Glow from Facebook, NN Fusion from Microsoft, and XLA from Google, and so on. So what are DL compilers? In a nutshell, they take trained DNN models as input, and they convert it to an internal graph-aware intermediate representation, which means that the computational graph semantics of the input model is preserved. And based on that IR, they can do graph level and low level optimizations to the model. Finally, they produce a compiled binary as the output, which we call DNN executables. So although there have been a bunch of DL compilers right now, they are relatively still a new thing, which means that they do not yet have the time to consider the security aspects of the compiled binaries. And at this point, if we take a look back at the traditional software, we can see that these traditional compilers already come with a number of security hardening techniques. For example, address sanitizers, ASAN, and undefined behavior sanitizer, OBSan, and many more. They are designed to detect and intercept the abnormal behaviors in the compiled binaries. However, they still don't have their counterparts in the world of DNN executables yet. There are no prior works to protect DNN executables. But at this point, you may also think, well, can't we just enable ASAN again? I mean, they've worked really well on those traditional binaries, and they should work just as well on those new binaries, right? Or alternatively, I think we should ask the question of what protection do DNN executables need? So to answer that question, we can take a look at the characteristics of DNN executables. Firstly, they are mostly machine-generated code, which means that they're not written by human, so they're not that error-prone. And then they're mostly for mathematical functions, which means that they're pure, and they won't do something like interacting with the rest of your OS. So these two factors decide that the anomalies in DNN executables often do not show up in code, but instead they are encoded in the concrete data values that are generated throughout the execution of the binaries. Therefore, traditional techniques like ASAN are not very suitable for this case. So to generalize the idea of anomalies in data values, we call this kind of anomalies out-of-bound behaviors. Typically, they cause the DNN model to produce some undesired outputs. For example, for a classifier model, it could be something like a wrong classification result. And the idea here is that for DNN models, their normal behaviors can be captured by some metrics that are bounded. For example, we have the neuron activation values in the forward propagation procedure, propagation process. And then we also have the gradients in the back propagation process. So if those metrics go out of their bounds, we'll consider that those models are having some abnormal behaviors. And actually, that's also our motivation to design OBSan. It captures the normal behaviors of the DNN models and then send out alerts when OOB behaviors are discovered in the binaries. To the best of our knowledge, it's the first work here to harden DNN executables. And we envision it to have a wide range of use cases like detecting unwanted inputs, mitigating black box attacks, and enabling feedback-driven fuzzing, and so on. So at this point, you may also think, well, there have been many prior works that focus on the detection of adversarial examples, or AEs. And that's true. However, according to our preliminary study, we found that it's difficult to apply them directly to the case of DNN executables. There are various reasons, and one major reason is that they frequently introduce operations that are not supported by DL compilers. For example, matrix inversion, set operations, and training new models. Another reason is that they focus more on the effectiveness aspect of the detection method, but they don't emphasize as much in the efficiency aspect. However, for the DNN executables case, we know that efficiency is important, and one big reason why we want to use DL compilers is because the better optimizations and better speeds that it provides. So back to OBSan here. Based on the two bounds we introduced before, we designed two variants of OBSan. We have FOBSan, based on the forward neuron activations, and then we have BOBSan, based on the backward gradients. Currently, we implement OBSan on TVM, but it's extensible and can be ported to other DL compilers as needed. So here's the overall workflow for OBSan. And we start with the unprotected original model as the input, and we'll feed it to the TVM and OBSan's front-end optimizations. Then TVM will lower it to relay IR, which is TVM's internal graph-aware IR. And based on that IR, OBSan can begin the instrumentation process for the model. So there are two modes for OBSan's instrumentation. They are detect mode and record mode, which have different final outputs. So for BOBSan, the backward variant, we instrument the model directly in detect mode. And after instrumentation, the model will go through OBSan's optimizations and then TVM's other optimizations. And finally, it will be built as an hardened executable. But on the other hand, for FOBSan, the forward variant, we additionally need to instrument the model in record mode to produce an auxiliary recorder executable. So with that executable, we can initialize the so-called normal bounds data for the protected model. And once that data is recorded, we feed it back again to the detect mode to produce the final hardened executable. So if we compare the unprotected and the final hardened executable here, we can see that it takes the same input and they produce the same prediction results. But for the hardened executable, it additionally provides the OOB information, for example, the OOB suspicion score for the input. And for evaluation, we use 4 types of different inputs to evaluate OBSan's capabilities to detect OOB behaviors. We have normal inputs, broken inputs, adversarial examples, and undefined inputs. Here, undefined inputs are inputs from another class that the original model is not trained on. So they represent knowledge that is unknown to the original model. And while while adversarial examples are most frequently related to the security aspects of DNN executables, we want to use other types of abnormal inputs too, because they are also related to the dependability and reliability of the model. So on the right, we have the results. And interestingly, we found that the two variants of OBSan react differently to different types of inputs. So for the first two figures, they are the results for FOBSan. And from this figure, you can see that FOBSan performs really well in terms of AE and broken inputs. But for undefined inputs, it does not have the ability to distinguish undefined inputs from normal inputs. And on the right, we have the results for BobSan, where you can see that it also does very well in distinguishing AE. Plus, it also has the ability to distinguish undefined inputs from normal inputs. But in terms of broken inputs, it is not as effective as FOBSan. But overall, we can report that OBSan provides very high capabilities to detect AE, and it also have very low false positive, meaning that it seldom interrupts the use of normal users. So in terms of performance overhead, we have three optimization schemes to lower the overhead of OBSan. There are quantization, security checks debloating, which is the removal of unimportant checks inserted by OBSan, and also parameter optimization, which is specifically designed for BobSan. So with all these optimizations enabled, we are able to lower the overhead of FOBSan from 121% to 48%, and that of BobSan to minus 34%, where here a minus percentage means that the protected model is even faster than the original. And this is mainly because the quantization process we employ is a global optimization applied to the model as a whole. So in addition, we also compared OBSan with existing methods, and we found that OBSan is faster than the most accurate methods that we tested in our experiments, and it also is more accurate than those fastest methods. So we say that OBSan strikes a balance between the performance overhead and detection effectiveness. And before I end this presentation, I also like to share some downstream applications that will be enabled by OBSan. The first we have here is feedback-driven fuzzing. And in this task, we extend OBSan to output the neuron coverage data instead of the suspicion score. And the result is that we found that the fuzzer is able to trigger 10 times more mispredictions on the binaries that are instrumented by OBSan. This is a sign of effective fuzzing. Another downstream application we have is online AE attack mitigation. And in this attack, we assume the attacker to use a state-of-the-art black box AE generation algorithm with no access to the model parameters. So to generate AE inputs, the attacker will need to send lots of queries to the model and then analyze the output of the model. To provide maximum protection, we also extend OBSan in this step, and we combine FOBSan and BobSan together to form the hybrid OBSan. The result is that up to 95% of the attacks can be intercepted, and up to 9 times more queries are needed for the attacker to generate an AE example, an AE input. So in this paper, we talked about the emerging trend of DNN executables, their need for more security protection, And we proposed OBSan, the first work here, to Harden DNN Executables. And we shared many details on the project, but we also believe that it has much more potential to be discovered. So if you are interested, you can check out the source code and other materials here. Thank you.
I didn't quite catch how you define the bounds based on the normal examples. Could you basically take that again? Because I'm trying to think about how is this different from just click gradient, click A, essentially. Like you set the value, but I guess the question is where do you set the value?
Okay, thank you for the great question. I think that would involve a bit of the details on the project. So I'll try to put it simply. So for example, for the forward variant, when you feed an input through the model, the neurons inside the model will have the activations values of their own. So if we have the training data set, we can feed them all through the model, and then we'll have a brief idea of how the neurons are activated by the training data. Right? So we can, based on those data, we can form the bounds.
Right, so you would need the entire training data, or some portion at least of the training data set in order to set this like baseline, essentially.
Yes, that is one of our assumptions. And yeah.
Thank you. Other question?
Hey, thanks a lot for this very interesting presentation. Just one question. Did you consider also white box attacks that basically adapt to the mechanism and try to avoid basically exceeding the boundaries for adversarial examples?
Let me see if I get your question. So at the end I talk about black box attacks, so you're asking whether I've also considered white box. Yes, we did. And actually in the evaluation part, the adversarial examples we use are generated with white box algorithms like PGD. So yes, OBSan also performs pretty well on that.
Okay, also I have another question. So how could techniques like batch normalization affect a new system? Basically by normalizing when it comes to out-of-balance behavior detection.
I'm sorry, you say the technique of what?
Batch normalization.
Batch normalization. Thank you for the interesting question. And I think here I don't think batch normalization will be a great obstacle for OBSan. Because the bounds that it recorded is according to the expected benign data provided by the developer or like model vendors. So they are supposed to capture the benign behaviors of their expected users. So for other kinds of abnormal inputs, I think OBSan can also detect their out-of-bound behaviors.